Welcome to the Thinking Abyss podcast, a philosophical journey through consciousness, reality, and the phenomena that challenge our understanding of existence. From ancient wisdom to cutting-edge theories, we explore where philosophy meets science and curiosity leads to the edge of the unknown.
I want you to try and visualize something for a second. While it's sitting right there, right behind your eyes.
We're starting with the glamour shots right out of the gate, I see.
You know it. But seriously, it weighs about, 1.4 kilograms?
Roughly, yeah. For most people, it looks a bit like a wrinkled walnut, or maybe some gray jello.
Exactly. It's unassuming, it's wet, it's biological. But here's the thing that absolutely breaks my brain every single time I think about it.
Okay.
Inside that wet biological mass, there are 86 billion neurons.
86 billion, which is a staggering number on its own. Just to give that some context, that is roughly comparable to the number of stars in the Milky Way galaxy.
The entire galaxy.
The entire galaxy.
All right.
All of that complexity condensed into the space between your ears.
That's just, it's hard to even start with that. But that's not even the scary number, is it?
No. That's just the count of the components. That's like counting the number of people in a city.
Right. The scary number is the connections, the conversations, the synapses. Because those 86 billion neurons are all talking to each other. And the estimates for how many connections there are? 100 trillion.
100 trillion. Mm-hmm. It's a number so large it effectively becomes abstract. It's really hard to wrap your head around what that even means.
I can't.
Think about it this way. It's more than the number of leaves on all the trees in the entire Amazon rainforest. By a lot.
That's insane. I can't even picture it. But you're telling me that this specific unique tangle of 100 trillion connections, that is me.
That's the operating theory, yes.
That's my memory of my first bike ride. That's my anxiety about this recording right now. That's my entire personality.
That is the physical basis of you. Everything you are, your capacity to love, your fear of heights, your ability to understand the sentence I'm speaking right now, it's all encoded in the physical architecture of those connections.
So it's not some ghost in the machine. It is the machine.
It is the machine. The central dogma of modern neuroscience is, essentially, you are your connectome.
And yet, and this is the part that we're going to really unpack today, for almost all of human history, we have had absolutely no idea how it's actually wired.
Virtually none. We've been completely flying blind. It's been a total black box.
It's like, okay, imagine trying to understand how the entire internet works, right? How information flows around the globe. But the only tool you have is the ability to look at 5 random routers in a basement in Ohio.
That's a great analogy. It really is. Or another one I like. Consider trying to understand the incredible complexity of New York City, the traffic patterns, the economy, the culture, the energy flow.
Everything that makes it tick.
Everything. But you're only allowed to study a single brick in a single wall of a single building.
Wow.
For most of the history of neuroscience, we have been studying the brick. We know what a neuron looks like. We know the chemistry, how it fires. We understand the action potential. But we haven't seen the city. We haven't seen the map.
But that is changing, and that is what we are talking about today. We are exploring what might be the most ambitious scientific project of our lifetimes, maybe ever. It's called the Connectome Project.
This is the mission, to map every single one of those connections, to verify every handshake between those 86 billion neurons, to build, for the first time, a complete wiring diagram of the mind.
It sounds impossible.
It was impossible. For a very long time, it was pure science fiction, until very, very recently.
So today, we are going to look at how on earth you map a ghost. We're going to look at the impossible technology required to see things that are barely there. We're going to look at worms and flies, and eventually the map of the human mind.
And we are going to ask the big question at the end of all of it. If we get this map, if we can finally read the blueprint of the brain, do we solve the mystery of consciousness?
Or do we just end up with a really, really complicated map that we still don't understand? Let's get into it.
Let's do it.
Okay, first things first. We need to define our terms properly. The connectome. It sounds cool. It sounds futuristic. I'm assuming it's a riff on genome.
Exactly.
Yeah.
You got it. Think back to the Human Genome Project in the 1990s, in the early 2000s. That was this massive global effort to map the complete sequence of our DNA, all the A's, C's, T's, and G's.
A book of life.
Book of life. The connectome is the parallel concept for neuroscience. It is the complete comprehensive wiring diagram of a nervous system.
And when you say wiring diagram, you don't just mean a sketch. You're not talking about a cartoon drawing in a textbook.
Oh no. I mean a full three-dimensional reconstruction of every neuron, every axon that sends a signal, every dendrite that receives one, and critically, every single synapse where they connect.
Every single one.
It is an anatomical map, but at a level of detail that is just. It's almost suffocating to think about. Some have called it mapping the hardware of the soul.
It's funny because I think most people, myself included, kind of assume we already have maps of the brain. I can go to a doctor's office and see a poster on the wall. There's the frontal lobe, there's the cerebellum. We know where the veins are.
We do. And that's not nothing. Anatomists mapped the gross structures of the body centuries ago. We know where the liver is. We know how the heart valves connect to the major arteries. And we do know the gross anatomy of the brain, the big regions.
But that's like knowing that New York City has 5 boroughs.
Precisely. That doesn't tell you how to get from a specific apartment in Brooklyn to a specific coffee shop in Queens. It doesn't tell you about the one-way streets or the subway lines.
Right.
The connectome isn't just the street view. Actually, no, it's far more detailed than that. It's the blueprint of every house, every room in every house, and every single electrical socket in every room.
Wow.
It's the schematic that tells you exactly where the electricity flows.
And the reason we want this, the core thesis of this entire field, is this phrase I keep seeing again and again in the research. Structure determines function.
Right. This is a fundamental rule in, well, everything. In biology and in engineering. The shape of a bridge determines how much weight it can hold. If you look at a suspension bridge versus, say, an arch bridge, you know they function differently because they're built differently.
The layout of a city determines where the traffic jams are going to be at 5 p.m.
Exactly. So the argument is, if the brain is a machine for processing information, which it is, then the physical way it is wired, which specific neuron connects to which other specific neuron, must determine how we think, how we learn, and ultimately who we are. If we can see the structure, we can finally understand the function.
It seems so logical when you put it like that, but getting there, I mean, we're talking about a scale problem that is just baffling. Let's talk about the impossible technology. Why has this taken so long? We've had microscopes for hundreds of years.
We have, but we run into a fundamental, unavoidable law of physics. The problem is what we're trying to see. We're trying to see a synapse.
That little gap between 2 neurons.
That tiny gap where the signal jumps, it is about 20 nanometers across.
20 nanometers. I have no frame of reference for that.
Almost nobody does. It is infinitesimally small. Now, the problem is visible light. The light we see with the light that's used in a standard high school microscope travels in waves.
Right.
Physics tells us that that wavelength is roughly 400 to 700 nanometers.
Wait, let me process that. So the light wave itself is literally too chubby to fit in the gap you're trying to look at.
In a manner speaking, yes, that's a perfect way to put it.
Yeah.
The wavelength of your probe, the light, is orders of magnitude larger than the object you are trying to resolve.
So it just washes over it.
It washes over. It's like trying to feel the individual bumps on a braille page while you're wearing oven mitts. The mitts are just too thick. You can't feel the fine detail. You just feel a smooth surface.
So if I look at a synapse with a normal, powerful microscope, what do I actually see?
A blur, a smudge. You know there's something there, but you cannot resolve the 2 sides of the connection. It's physically impossible due to what's called the diffraction limit of light.
So you can't just zoom in more.
You cannot. You need a probe with a smaller wavelength. You need to take off the oven mitts. You need electrons.
Enter the electron microscope.
Exactly. Beams of electrons have much, much shorter wavelengths than photons of light, orders of magnitude shorter. So with an electron microscope, we can finally see down to the nanometer scale. We can see the synapse. We can see the tiny vesicles that hold the neurotransmitters. We can see the machinery.
Soft. Let's go map a brain.
Problem just beginning. Because an electron microscope isn't like a camera you can just point at a living brain. Electrons, unfortunately, don't penetrate thick tissue. They're very easily stopped. They either bounce off the surface or get absorbed almost immediately. So if you want to see the inside of the brain, you have to slice it.
Slice it.
You have to slice the brain tissue into sections that are almost unimaginably thin. We were talking 30 to 50 nanometers thick.
Okay, to put that in perspective again, how thick is a single human hair?
A human hair is maybe 80,000 to 100,000 nanometers thick.
So, wow, so we are slicing tissue thousands of times thinner than a single strand of hair.
Yes. Imagine taking a loaf of bread. But the slices are so thin, they are effectively invisible to the naked eye. You'd need a microscope just to see the slice itself.
And you have to slice the whole brain or the whole piece you're studying.
If you want a whole connectome, yes,
Yeah.
the whole thing. And you cannot lose a single slice. You can't have a tear, you can't have a wrinkle, because if you lose one slice, you sever the connection in your data. You lose the wire.
It's like reading a book and someone rips out page 157. You completely lose the plot.
You lose the plot. In the brain, if you lose a slice, you lose the circuit. The neuron on slice 156 has nowhere to connect to on slice 158. It's a broken link.
That sounds incredibly stressful for the grad student doing the slicing.
It is incredibly high-stakes work. The tissue has to be preserved perfectly, stained with heavy metals, things like osmium and uranium, so the electrons will bounce off the cell membranes. Then it's embedded in a hard plastic resin like a piece of amber. Then you use a diamond knife.
Literally a diamond.
Literally a sharpened diamond to cut these ultra-thin slices, which are then floated onto a tiny pool of water and collected one by one.
My God. And then, once you have these millions of slices, you have to image each one individually with the electron microscope. And then, and this has to be the kicker, you have to digitally stack them all back together.
The Humpty Dumpty phase, yeah.
You have to put the brain back together again.
You have to take these thousands or millions of 2D images and align them perfectly to reconstruct the 3D volume. And then the real work begins. This is called segmentation.
Which is the coloring in part.
It's the coloring in part. You are digitally tracing a single neuron that starts in slice number 1. See it wind its way through slice 500. Then it branches out in slice 5,000.
And remember, there are billions of them, all tangled together like a bowl of spaghetti.
The data explosion is catastrophic.
Yeah.
A single cubic millimeter of brain tissue, just a tiny speck the size of a grain of coarse sand, contains about 100,000 neurons and a billion synapses.
A billion synapses in a grain of sand.
And the images are massive, 10,000 by 10,000 pixels each. We're talking petabytes of data for a tiny piece of a mouse brain.
I read in the notes that for the longest time, the bottleneck wasn't even the slicing or the camera, it was the tracing.
Oh, absolutely. For decades. In the early days, this was pure, painful manual labor. It was graduate students with actual colored pencils tracing on giant printouts of the images. Later, it was with digital tablets sitting there coloring in the shape of the neuron on the screen, slice by slice by slice.
Okay, here's the little circle in slice 1. Now let me find the corresponding circle in slice 2.
For hours, for days, for years, it was completely impossible to scale. They did a calculation that if we tried to map an entire human brain by hand, just the tracing part, it would take millions of person years.
Millions.
They would need the entire population of a large country working 2047 for years just to trace one brain. It was a non-starter.
So what changed? Because we are talking about this now, so something must have happened in the last decade or so, in the 2010s.
The AI revolution. That's the simple answer. We finally got computer algorithms that could see in a sophisticated way. Deep learning, specifically convolutional neural networks. We trained computers by showing them millions of examples of what a neuron boundary looks like in these grayscale electron microscope images.
So the AI does the coloring now.
The AI does the heavy lifting, yes.
Yeah.
It automatically segments the image. It looks at the whole mess and says, okay, I think this blob belongs to neuron A, and this adjacent blob belongs to neuron B. It traces the boundaries for us.
Is it perfect?
No, not at all. It makes mistakes. So humans still have to come in and check it, kind of like proofreading an essay written by a machine. But it sped the process up by orders of magnitude. It turned a task that would take 1,000 years into a task that takes a few weeks or months. It made the impossible possible.
And I guess the physical technology got better too, the slicing and imaging.
It did. We developed new machines for serial section electron microscopy, which could automate the process of slicing and imaging. And something even wilder called FIB-SEM-focused ion beam scanning electron microscopy.
That sounds like a weapon from Star Trek.
It's pretty intense. It uses a laser-like beam of ions, gallium ions usually, to essentially vaporize, to ablate a tiny layer off the surface of the plastic block. It takes a picture, then vaporizes the next layer, takes a picture.
So it destroys the sample as it reads it.
Yes. It eats the tissue to map it. It is destructive scanning. Once you've mapped that piece of brain, the physical object is gone. It only exists as data on a hard drive.
That is metal, literally and figuratively. Okay, so the tech is finally here. We have the fancy microscopes, we have the diamond knives, we have the AI tracers. Let's talk about the roadmap, because we didn't just jump straight to humans. We started small.
Very, very small. We started with the worm, Caenorhabditis elegans,
The humble roundworm.
the unsung hero of biology. C. elegans is tiny, about 1 millimeter long. You can barely see it. And it has an amazing property. It is incredibly consistent. Every single worm has the exact same number of neurons,
Which is
302.
302. That's it. I feel like I could memorize 302 names. My high school was bigger than that.
You probably could. And yet, mapping the connectome of this tiny worm, just 302 neurons and about 7,000 synapses, took over a decade of continuous work.
A full decade.
It was finally finished and published in 1986. Sidney Brenner and his colleagues. And remember, this was before any of the AI tools. This was the dark ages. It was pure manual labor. They were physically tracing the lines on printed photographs of electron microscopy slices stacked in a room.
That sounds like madness, like something out of a conspiracy movie.
It's a Herculean effort, one of the great scientific achievements of the 20th century. But they did it. They got the map, the first complete wiring diagram of any living organism. And it taught us something profound and a little bit humbling.
Which was?
That knowing the wiring isn't enough to predict everything.
Wait, you just spent 10 minutes telling me the thesis was structure determines function.
It does. It absolutely does. But it's not the whole story. What they found was, even with the perfect, complete map of the worm, they couldn't predict its behavior 100% of the time.
Why not?
Because the network state is not just about the wires. There are chemicals, neuromodulators, that bathe the whole system and can change the properties of the connections on the fly.
So a wire might exist, but a chemical signal can turn its volume down to 0.
Precisely. The wiring constrains behavior. It sets the absolute limits of what the worm is capable of doing, but it doesn't dictate it moment to moment like a simple clockwork toy. It's a much more dynamic system. But still, the worm was the essential proof of concept. It showed it could be done.
Okay, so we conquered the worm in the 80s. Then things went pretty quiet for a while, I guess, until the tech caught up. And then came the next big one, the fruit fly.
Drosophila melanogaster. This was a very recent breakthrough, published in 2020. This is a massive, massive leap forward.
How big of a leap are we talking?
Well, the fly has about 100,000 neurons.
So we went from about 300 to 100,000. That's a huge jump.
And from 7,000 synapses to about 30 million synapses. The data scale was just enormous, over 100 terabytes of raw image data. This project required a massive collaboration between the Genelia Research Campus and Google. Google provided the computing power and the AI expertise to actually crunch the data and do the automated segmentation. There was no other way.
So this was the moment where the automated imaging and the AI really had to flex their muscles on a big project.
Correct. They proved that the entire pipeline worked at a serious scale, and the insights were incredible. They could map the entire visual system of the fly, showing how the information from the eyes flows through different processing centers. They found the circuits for navigation.
Navigation, like how it flies around.
Yes. They found a specific ring of neurons in the central complex of the fly brain that acts like a biological compass. As the fly turns its body, a little bump of neural activity moves around this ring. It literally tracks its heading in the world.
That is amazing. You can see the compass.
You can see the compass, and you can see the wires that make it work. They also identified hardwired circuits that are basically identical in every single fly, like the basic operating system, and fascinatingly, variable regions that differ from fly to fly.
Wait, variable regions?
Yes, connections that were present in one fly but not another.
So that's like fly personality. Is that too big of a leap?
It's a bit of a leap, but it's the right direction to be thinking in. It's, at the very least, the basis for individual differences in behavior. It showed that not every brain is stamped from the exact same mold, even in a creature as seemingly simple as a fruit fly. The wiring has some randomness, or maybe it's customized based on that fly's life experiences.
That is wild. Okay, so we have the worm, we have the fly. Now we're moving up the evolutionary ladder into the vertebrate world. Creatures with backbones, creatures a little bit more like us.
And here we meet the zebrafish.
The zebrafish larva. I've seen these in pet stores, little striped guys. Why them?
For one very simple, very beautiful reason. The larva is transparent.
Transparent, like the Invisible Man transparent.
See-through skin, see-through skull. You could put it under a microscope and look right at its brain while it is alive and swimming around.
That seems almost unfairly convenient for science.
It is the Rosetta Stone opportunity. Because with the worm and the fly, we had to slice them up to map them. They were dead. We had the structure, the map of the roads, but we couldn't see the traffic flowing on those roads in real time.
Right, you just had the road map. You didn't know if it was rush hour or 3 in the morning.
With the zebrafish, because it's transparent, we can use advanced optical microscopes to watch the neurons actually firing. We can make them flash green with calcium indicators. While the fish is thinking and moving and reacting to things, we get the function.
I see where this is going.
Then we can take that very same fish, preserve it, slice it up, and get the structure with the electron microscope.
So you can literally overlay the traffic map onto the road map.
Exactly. We can finally see how the computer actually processes the data. We can say, oh, when the fish sees a predator, this specific wire lights up, which in turn triggers this hub neuron, which then activates the circuit that makes the tail flip. It's the first time we can truly integrate the two views, structure and function, in a vertebrate.
That is incredibly cool. But a fish is still a fish. We want to get to mammals. We want to get to the mouse.
The mouse is the next boss level.
The mammalian challenge.
A mouse brain is roughly 1,000 times larger than a fly brain. We're talking about 70 million neurons. The whole thing is just, it's on another level of complexity.
The exponential jumps here are getting out of hand.
It's terrifying from a data perspective. We are nowhere near a full mouse connectome yet. The Max Planck Institute in Germany has a mouse connectome project, but they're taking a more targeted approach. They're mapping specific important regions. They're doing the visual cortex or a piece of the motor cortex.
And what are they finding? Is a mouse brain just a really big fly brain, or is it fundamentally different?
It seems to be different. It's denser. It's messier in a way. The complexity of the connections, the number of feedback loops in mammals is much, much higher. Invertebrates like flies have very efficient, very clear feed-forward modules. Mammals seem to have a lot more crosstalk, a lot more integration between different systems.
Which brings us inevitably to the human brain.
The ultimate goal.
But based on what you just said, if we can barely do a small piece of a mouse, slicing up a whole human brain seems completely impossible right now.
The microscopic approach, slicing a whole human brain with an electron microscope, is currently pure science fiction, the data size.
Yeah.
You're not talking petabytes anymore, you're talking exabytes. It would take decades, maybe centuries, to image with current technology.
And that's before even talking about the ethical issues.
Exactly. You would need a pristine brain, perfectly preserved, within minutes of death. That's incredibly difficult to acquire.
So we can't do the slicing method for humans yet. But I hear about the Human Connectome Project all the time in the news. If they aren't slicing brains, what are they doing?
This is the crucial distinction that everyone needs to understand. There are two very different ways to map a connectome. Approach A is what we've been discussing.
Yeah.
The slicing, the electron microscopes, that's the micromap, the synaptic level map.
Right.
Approach B is the macromap. This is what the big, publicly funded Human Connectome Project does. They use MRI scanners on living people.
Okay, so a totally different technology.
Totally different. Specifically, they use a technique called DTI diffusion tensor imaging.
DTI? How does that work? It doesn't sound like it's taking a picture of a synapse.
It isn't. It's much cleverer than that. It tracks the movement of water molecules in your brain. It turns out that water diffuses. It flows more easily along a big bundle of nerve fibers than it does across it.
Like water flowing down a hosepipe is easier than it flowing through the wall of the hosepipe.
That's the perfect analogy. So by tracking the direction that water is flowing, the MRI can trace the path of the big bundles of white matter cables in your brain. The information's superhighways.
So it shows the highways?
Exactly. To go back to our city analogy, the micro method maps every house, every driveway, every single alleyway. The macro method maps the interstate highway system.
Okay, that's a really helpful way to think about it.
The macro map won't show you a single synapse. It won't show you individual neurons, but it shows you how the frontal lobe connects to the parietal lobe. It shows you the grand architecture of the brain. And the best part is, we can do it on thousands of living, breathing people. You can go get your macroconnectome scan right now.
So when we talk about the human connectome today in 2024, we're usually talking about this highway map, not the street level map.
Correct. But even that highway map has been absolutely revolutionary. It's the first time we've seen the human brain not as a collection of disconnected blobs, but as a single integrated network.
So we have these maps. We have the full worm map, the full fly map, bits and pieces of the mouse, and this new highway map of the human. The big question is, what if we actually learned from all this? Are there rules to the wiring? Or is it just a tangled mess of spaghetti in there?
It is definitely not spaghetti. It is a highly, highly organized structure. And yes, we have started to identify what you might call the 6 laws of neural wiring.
Okay, I love a good list of rules. Let's walk through these. Principle number 1, modularity.
The brain is like a collection of cities. We call them modules. You have a module for processing vision, a module for controlling movement, a module for understanding language.
And inside each of those cities, everyone knows everyone. The connections are dense.
Right. The connections within a module are very dense and numerous, but the connections between the modules, the long-distance connections, are sparser. It's an efficient design. You don't need your toe-wiggling neurons to be constantly talking to your algebra-solving neurons.
They stay in their lane for the most part. Okay, that makes sense. Principle number 2, hub neurons.
These are the influencers of the brain,
The Kardashians of the cortex, I think I read somewhere.
if you will. It's not a bad analogy. Most neurons are fairly local. They only connect to a few hundred or a few thousand neighbors.
Yeah.
But some neurons, the hubs, have a massive number of connections. They connect to hundreds of thousands of others, often across different modules.
So they're the bridges between the cities.
They are the bridges. They integrate information from all over the network. They're critical for coherent thought and consciousness. But this design also sounds important, but also very risky.
How so?
It's a huge vulnerability. If you lose a random non-hub neuron, the network is fine. It's resilient. It can route around the damage. But if you damage a hub, the whole network can crash, or at least become severely impaired. We think this is key to understanding many brain diseases.
We'll definitely come back to that. Okay, principle number 3, repeating motifs.
The brain uses Lego bricks to build itself.
Explain that.
When we look at the wiring diagrams up close, we see the same little patterns of circuitry repeating over and over and over again all across the brain. A little triangle of 3 neurons connected in a specific loop. A feed-forward chain. These are called motifs.
And these little Lego bricks, these motifs, they each do a specific job.
That's the theory, exactly. One specific motif might be really good at amplifying a weak signal. Another might be designed to filter out background noise. The brain just copies and pastes these little pre-designed computational units wherever it needs them. It suggests the brain is built from a set of standard components, not just random wiring.
That's incredibly elegant. It's modular design all the way down. Okay, principle number 4, the dense-sparse paradox.
This one is a little tricky to get your head around, but it's crucial. Locally, at the microscale, the brain is incredibly dense. But globally, at the macro scale, it is surprisingly sparse.
What do you mean by sparse? There are 100 trillion connections. That doesn't sound sparse.
It doesn't. But think about the potential connections. If you calculate all the possible connections between 86 billion neurons, the number is astronomical. If every neuron connected to every other neuron, your brain would need to be the size of a building to hold all the wiring, and it would consume all the energy in your body in seconds just to maintain it.
So it can't be fully connected. It's not physically or energetically possible.
Exactly. So evolution solved this problem by making it sparse. Most neurons are not directly connected to most other neurons. Each neuron is only connected to a tiny fraction of the whole. It's a brilliant energy-saving strategy.
It's the small world network idea, right? You're only 6 degrees of separation from Kevin Bacon, but you don't actually know Kevin Bacon personally.
That is the perfect way to put it. You can get a signal from one side of the brain to the other in just a few hops, thanks to the hubs we talked about, but you don't need a direct wire connecting everything to everything else.
Okay, that's clever. Principle number 5, redundancy and robustness.
This is the brain's backup plan. Nature hates a single point of failure. The brain rarely has just one single wire or pathway doing a critical job. It has multiple parallel pathways.
Which is why you can have a minor stroke or a head injury and not necessarily have a catastrophic failure.
Precisely. The brain can reroute the traffic. It's robust. If the main highway is closed for construction, you take the side streets. It might be a bit slower, you might be a bit impaired, but you can still get there.
And finally, principle number 6, which brings us full circle. Structure predicts function.
We're circling back to the core thesis. And in the Fly visual system, they proved it beyond a shadow of a doubt. If you know the wiring diagram of the visual system, you can build a computer model of it, and you can accurately predict how the fly's neurons will fire when it sees certain patterns.
So you can look at the map and say, based on this wiring, this fly is currently looking at a vertical line moving to the left, just by looking at the wires.
Just by looking at the wires. That is the proof that this whole massive, expensive, decades-long project isn't a waste of time. The map really does tell you how the machine works.
Which leads us to the part where we ask, why should the listener really care? Beyond the fact that this is incredibly cool science, how does this actually change our life?
The biggest and most immediate impact is going to be in mental health and psychiatry. It's going to cause a revolution.
How so? We usually think of disorders like depression or schizophrenia as chemical imbalances. We take SSRIs to boost serotonin levels.
That has been the dominant model for 50 years. I call it the brain soup model. The idea is that the brain is a soup of chemicals, and for some reason the soup is too salty, so we add some sugar to balance it out.
It's a bit crude when you put it like that.
It is crude, and it often doesn't work that well. The Connectome suggests a much more precise model, that these disorders are not just chemical imbalances, they are connectopathies.
Connectopathies. I like that. Wiring errors.
Exactly. Schizophrenia, for example, when you look at the brain scans, it doesn't look like a global chemical problem. It looks like a breakdown of specific hub neurons or the disintegration of specific white matter tracks that connect the reality testing parts of the brain in the prefrontal cortex to the auditory parts.
So the hearing voices symptom is literally a crossed wire or a short circuit.
Potentially. Or a wire that has lost its insulation, its myelin sheath. If we start to view these illnesses as circuit problems, we can stop just bathing the whole brain in drugs that have side effects everywhere. We can start looking for ways to target and modulate specific faulty circuits.
Precision psychiatry.
That's the term. Things like deep brain stimulation are already doing this for Parkinson's and severe depression. But right now, it's a bit of trial and error where they place the electrode. If we have the map, we will know exactly where to put the electrode to fix the circuit. We stop guessing.
That's huge. What about something like autism?
Autism is a fascinating case through the lens of the Connectome. One of the leading theories, backed by a lot of imaging data, is that it involves hyperconnectivity locally, super intense, detailed wiring within sensory modules, but hypoconnectivity, globally weaker long-range connections between modules.
So you get this incredibly intense focus on the sensory details of the world, but it's harder to integrate that information into a coherent big picture.
That matches the lived clinical experience of many autistic people perfectly. And seeing it in the wiring validates that it's a real physical structural difference in the brain, not just a behavior or a choice. It's a difference in hardware.
Okay, let's shift gears. What about brain-computer interfaces? BCI, we hear about companies like Neuralink and all this futuristic stuff.
If you want to plug a computer into a brain, you need the pin-out diagram. You need to know which wire carries the signal for move left arm versus think about the color blue. The Connectome is that diagram. It's the technical manual for the brain.
So this could lead to prosthetics that actually feel, that can send touch signals back to the brain?
Absolutely. Or even more profoundly, communication for people with locked-in syndrome. If we can decode the wiring of their speech centers, we could potentially listen to their internal monologue, their intention to speak, and put the words on a screen for them.
That is sci-fi becoming reality right there. And then there's predictive medicine.
This is the dream for neurology. Imagine you get a routine Connectome scan at age 30 as part of your physical. The doctor looks at it and says, okay, we see a slight thinning of the connections in your hippocampus. This puts you at a high risk for developing Alzheimer's disease in 40 years. Let's start a preventative therapy right now.
Before you ever have a single symptom, before you ever forget where your keys are.
Right. Catching the structural decay long before the function fails. That's the holy grail.
I love this idea of the mystery of individuality, too. We touched on it with the fly personality. But my Connectome is unique, right? It's like a fingerprint.
It is absolutely unique. Even identical twins who have the exact same genome have very different connectomes.
Oh.
Because your connectome is not just built by your genes, it is shaped every single day by your experiences.
So every time I learn something new or form a memory...
or practice a skill like playing the piano, you are physically changing your synapses. You are strengthening some, weakening others, creating new ones. You are literally rewiring your own brain as you live your life.
I am the architect of my own Connectome.
You are. The wiring explains why you are you, why you're creative, why you might be susceptible to addiction, why you're good at math but bad at languages. It's all, at some level, physically encoded in the network. Sebastian Sung, who's a brilliant researcher in this field, has a famous saying, I am my Connectome.
It's empowering in a way. But let's play devil's advocate for a minute. We are painting a very rosy, optimistic picture. What are the hurdles? What's stopping us from having a full human map tomorrow?
The biggest, most boring, and most real hurdle is simply data. We talked about the petabyte.
1 million terabytes.
And that's a conservative estimate for a detailed human map. It might be even more. It might be exabytes.
Yeah.
We literally do not have the storage infrastructure or the processing power to handle a whole human brain at synaptic resolution right now. We need better, faster computers.
So we are waiting for our external computers to catch up so we can understand the biological computer in our heads.
Essentially, yes.
Yeah.
It's a bit ironic. And we're waiting for the scanning speed of the electron microscopes to improve. At the current speeds, just acquiring the images for a whole human brain would take decades of continuous beam time on a single machine.
And then there's the so what argument, the philosophical critique that the map isn't the territory.
This is the connectome is not enough argument.
Yeah.
And it's a very valid and important reality check. I can give you a perfect schematic of a vintage radio. I can show you every resistor, every wire, every capacitor.
The full blueprint.
The full blueprint. But if I don't tell you that there's an invisible radio signal coming in from the air, you will never, ever understand how it plays music. You'll just have a diagram of a silent box.
And in this analogy, the radio signal is our experience, or the chemicals.
It's both. The connectome, the map, doesn't show the neurotransmitters flowing. It doesn't show which genes are being expressed in which cells. Crucially, it doesn't show the firing rates of the neurons. It's a static map of an incredibly dynamic system.
It's a map of the hardware, but it doesn't come with the software that's running on it.
That's the single best way to put it. And some neuroscientists argue that we are obsessing over the cables when the real magic is in the software, the dynamic patterns of activity that flicker across the network.
But you need the hardware to run the software. The two aren't separate.
You do. You absolutely do. You can't understand the software if you don't know if it's running on a supercomputer or a pocket calculator. The map is necessary, but it might not be sufficient on its own to explain everything.
So let's be realistic. Timelines. When do we get a full mouse connectome?
A full synaptic level mouse brain. I think the consensus is probably 5 to 10 years. It's within reach.
When do we get the human?
Well, significant regions of the human brain, like a whole cubic millimeter of the cortex, probably 10 to 15 years. But a whole human brain, synapse by synapse.
Give me a number. Your best guess.
Optimistically, maybe 50 years. Pessimistically, never. We might just decide it's not worth the monumental effort. We might decide that sampling mapping many small representative pieces and extrapolating the rules is good enough.
Good enough isn't quite as inspiring as the complete map of the human mind.
Science is often about the art of the sufficient, not the pursuit of the absolute.
True. So as we wrap this up, let's zoom out. We started by talking about the almost spiritual complexity of you, the 100 trillion connections that make you who you are.
We are witnessing a deep philosophical shift in how we see ourselves. We are moving from observing human behavior from the outside, which is what psychology did for a century, to observing the actual machinery from the inside, which is what connectomics does.
Well, we're finally reading the blueprint.
We are. It is the ultimate act of introspection. Humanity holding up a mirror and finally seeing the intricate glass of the mirror itself, not just the reflection.
It still doesn't explain the hard problem of consciousness yet, does it? It doesn't explain why red looks like red or why love feels like love, the subjective experience.
No, it does not.
Yeah.
And it may never, but it provides the necessary constraint. Any future theory of consciousness must be compatible with the physical wiring. You can't have a valid theory of the mind that ignores the map of the brain. The map is the ground truth on which all other theories must be built.
Okay, here's a final thought I want to leave everyone with. A pretty provocative one.
Go for it.
If we get there, let's say in 50 or 100 years we do it. We map a complete human brain down to the last synapse. And we have computers powerful enough to upload that map, that entire 100 trillion connection-strong network, into a simulation. And we simulate the physics of every neuron, every synapse perfectly.
This is the singularity question, the mind uploading problem.
Is that simulation conscious? If I map your brain and I run it on a server in a warehouse, does that server have rights? Is it you? Or is it just a very clever echo?
If structure truly determines function, then the logical answer has to be yes. But that is a terrifying yes, with implications we have not even begun to grapple with as a species.
The Connectome Project brings that classic sci-fi question out of the movies and puts it on the table as a future engineering problem. And that is both the most exciting and the most absolutely terrifying thought I can imagine.
I think I'll stick to the fruit flies for now. It feels a little safer.
Probably a wise choice. Thank you for joining us on this journey through the wiring of the mind. Hopefully a few new connections were made in your own connectome over the last hour.
Keep thinking.
See you next time.